Hi, and welcome to today's how-to video, where we are going to work through a fairly common scenario faced by developers. That is, I've been asked to test some application code, but I don't have the environment to do the required testing. Our application under test is one that monitors the output of an analog to digital converter. Normally, this converter would be connected to a component such as a sensor that may report its output in terms of a voltage. To test this application, I will create a test harness that connects an SPC5 MCU VP, which contains an analog to digital converter, a fuel sensor to feed values into the converter, and a stimulus model to simulate conditions that the sensor can report on. One of the challenges that developers often face is not having access to real or even virtual components that are required. In the VLab environment, it is quite simple to create a Python systemc model that provides the functionality that you need to execute your test, and this is what we are going to use for both our fuel sensor and stimulus models. To keep our system simple, we will create a sensor that takes as input a percentage of how full a fuel tank is, and outputs the same value after being scaled to a voltage with a capacity of 5 volts. Driving the input of the sensor will be a stimulus model representing the level of the fuel tank. Over time, this will decrease in a random fashion, and when it reaches empty, it will be refilled. Here you can see in this Python module, we declare a class to represent our sensor, which will be instantiated as an instance in our simulation. As we described earlier, we have input and output ports, and here we create a callback method that will be invoked anytime there is an update on the input port. In the callback, it reads the incoming percentage, converts it to represent a voltage, and then writes this out. In a similar way, we create the stimulus model with an output port. However, this model spawns a thread that waits for a random time, decrements the simulated fuel level by a random amount, and sends this through to the sensor. If the level goes negative, then there is a simulated refilling of the tank. To connect these two new components to our SPC5 MCU, we need a test bench, where they are instantiated and then connected, stimulus to the sensor and sensor to the MCU. When using a test bench description such as this one that adds components to an existing virtual platform, it is necessary for these components to be instantiated during the elaboration phase. With the SPC5 VP, I can pass the test bench module as a parameter to the VLab load command to be processed. With all of the components now ready, I can run my test script that loads the complete test bench and application software ready for execution. In the system pane, you can see that we have our stimulus and sensor models, along with the MCU subsystem. When I run the simulation, you can see values being echoed to the console as the software is periodically responding to timed interrupts, where it reads the value from the sensor. Using these values that are being printed may be sufficient to validate test cases that you develop, but to better understand the behavior of the software, it helps if we can see the interaction of various elements over time. As part of my simulator setup, I added tracing to the stimulus and sensor outputs, the input port, a software variable which is toggled before and after the ADC does its conversion, and another variable with the converted value. These traces have been directed to a VCD file that we can view to show how the values change over time, such as the fuel level falling before being refilled. One other information point here is the timing between hardware and software events. For example, if we zoom in to view the PA1 out port, which is a hardware event, we see that shortly after, its value goes high. The converted variable also goes high, signaling within the driver code the start of the ADC conversion, and the update in software to the new digital value of the connected fuel sensor. If we now return to the original question of creating an environment suitable to complete our testing, one of the key advantages of using virtual components is being able to test the response to failure conditions that are either not feasible or possible with real test hardware. Using our sensor model as an example, we can simulate a failure for a period of time before recommencing and check how the software responds. To create this scenario, I will need 3 things. First, I create a breakpoint action that gets called in response to the sensor model output being written to, and will overwrite the update with a fixed value of 0. Second, I create a function that validates a conditional breakpoint. In this case, the function returns true, allowing the breakpoint to fire if the simulation time is in between 2 and 6 seconds, and returns false otherwise. And finally, I create a breakpoint that is conditionally triggered on an update to the sensor output port, and in response calls our fault callback action. If we now rerun the simulation and view the trace output, you can see how our fault scenario is being fulfilled, with the sensor output forced to a fixed value for a period before being restored. This is just one example of how you can quite easily create the conditions that you need to achieve the test coverage required. Within the VLAB documentation, there are many examples of modelling failures for bus faults and timing jitter, memory accesses, register writes, and even software execution. You can also find examples on how to quickly model components that you may need in Python or C++. If you would like some assistance in setting up your test environment using VLAB, then make contact through training@vlabworks.com. Alternatively, if you would like to organise a trial of VLAB running your software, email sales@vlabworks.com. Thank you for taking the time to watch this video, and keep a watch out for more at vlabworks.com.